Our next speaker is David Mateos, who's going to tell us about gravitational waves from the fifth dimension.
Thank you very much for having me. Thank you for inviting me. Thank you for organizing. It's a pleasure to be here with so many friends. So as you all know, we discovered gravitational waves in 2015. And this opened not one, but two actual experimental windows into the universe, two new ones. One into the strong field regime of gravity, and the other one into the properties of quantum matter. And one thing that's really interesting is that these two properties are very often intertwined. For example, if you think about a neutron-star merger, the system that you're describing is governed by quantum chromodynamics for quarks and gluons, coupled to the classical and very strong gravitational field, and very time-dependent, sourced by these quarks and gluons themselves. So in some cases, these systems producing gravitational waves are formed with standard model matter, as in neutron stars. In other cases, the putative matter is necessarily beyond the standard model matter, as you will see, as in cosmological phase transitions. So in order to maximize the discovery potential, we need to understand the properties of quantum matter coupled to dynamical gravity. And it turns out that this matter is often out of equilibrium, or far from equilibrium even, or strongly coupled, or both. And as you all know, this is a regime that's very hard to study with conventional field theoretical methods. But it's also a regime that contains much more microscopic information precisely because of the out of equilibrium properties than other systems. So it's very interesting to understand it. And in many cases, holography is the only first principle tool that allows you to do at least some first principle calculations. So what I want to do today is to give you an overview of possible applications of holography to cosmology and astrophysics with a focus on gravitational waves. And in the interest of time, I'm going to focus on the role played by first-order phase transitions. So just to get everybody on the same page, I'll say a few words about holography. Then I'll talk about phase transitions in cosmology and in neutron-star mergers. And in this part, I will ignore the dynamical aspects of gravity. That means that here I will imagine that the phase transition is very fast compared to the expansion rate of the universe. And here I will imagine that the length scales associated with the transition are much shorter than the typical curvature scale in the merger. So if time permits and the chair is nice, I will then, at the end of it, I'm not counting on it, but at the end of it, I will tell you how to go beyond this approximation and consider a new holographic framework in which gravity at the boundary is dynamical. And I will describe that with an application to the dual, the gravity dual, the holographic dual of primordial black hole formation. Before I do any of that, let me just advertise that there will be several PhD and postdoc positions, up to 4, in Barcelona this fall. So if you're applying this fall or you know people who are interested, please encourage him to write to me. That's the most important thing I had to say today. So in the remaining time, let's talk about holography. So for the purpose of this talk, holography is an exact equivalence between some quantum field theory, ordinary quantum field theory with no gravity, for the first part of the talk, in Minkowski space in 4 dimensions, and some classical theory of gravity in asymptotically ADS5. But it turns out that the boundary of ADS5 is isomorphic. It's a copy of Minkowski in 4 dimensions. So it's extremely useful and convenient to think of the duality as between gravity in 5 dimensions and some quantum field theory living at the boundary of that 5-dimensional space. Now, there are 2 things that you need to remember for this talk about holography. The first one is that if you're looking at thermal state, suppose you have some thermal state in equilibrium at the boundary, that corresponds to the presence of a black hole, an infinite black brane, sitting at the bottom of the geometry. And the crucial point is that if you want to go beyond thermal equilibrium, in particular arbitrarily far away from equilibrium in your quantum field theory, which is the regime that we don't know how to describe with quantum field theory, that corresponds, in the limit in which I'm working, to a very strong time-dependent situation in the bulk, but still a classical situation. Okay? So if you know how to do time evolution in classical gravity, then you know how to solve quantum field theory out of equilibrium in the limit that I'm working in. Now, a disclaimer is that we don't know the gravity dual for each quantum field theory we may be interested in. So all the statements that I'm going to make in this talk apply to theories that have such a holographic dual. It may not be all of them, but the hope is that since it's a large class, we may learn generic or robust properties that may be applicable more generally. Good. So let's talk about cosmological phase transitions. First order phase transitions, as you know, happen everywhere in nature. When you boil water, you have a first order phase transition, and they proceed via the nucleations of the preferred phase, the nucleation of bubbles of the preferred phase inside the metastable phase. So you may wonder whether they also happen in particle physics, and this would be great, because if they happen in particle physics, it means that the universe would have undergone such a phase transition in the history of the universe. And this would be very exciting because in first order phase transitions, these dynamics of bubbles, when they collide, etc., and leave behind excited modes, this produces gravitational waves that we may be able to detect today. And they may tell us properties of the early universe, for example. However, we believe that in the standard model of particle physics, there are no first order phase transitions because both the QCD transition and the electroweak transition, where the Higgs condenses, and this the confinement-deconfinement transition, they are both believed to be crossovers. For example, in this case, it's a rapid but smooth crossover, and this does not produce this out of equilibrium phenomena. So if you're a pessimist, this is kind of a bummer. But if you're an optimist like me, this is great, because this means that the discovery of gravitational waves coming from a cosmological first order phase transition is the discovery of physics beyond the standard model. And moreover, this may be our only window ever into those physics if the associated energy scale is high enough. It's very unlikely that we may be able to build a particle collider on Earth that may probe the same energies that are probed in the early universe. Good. So once these bubbles are nucleated and they expand and collide, all these processes produce gravitational waves. So we need to understand as well as possible the spectrum in order to be able to detect them and claim discovery. It turns out that the gravitational wave spectrum is sensitive to different properties of these first order phase transitions, but one that they are extremely sensitive to is the velocity with which these bubbles expand. Once they are nucleated with a microscopic size, they expand with a characteristic terminal velocity, and this plays a crucial role in determining the peak frequency at which you will get most of the gravitational waves. So it's really important to understand this. And at the same time, this is also the parameter that's hardest to compute, even in weakly coupled gauge theories. And the reason for that is as the bubble expands, it pushes the fluid outside out of equilibrium. So you cannot get this parameter from any thermodynamic calculation. This is fully dynamical. Okay? But it turns out it's really easy to compute it, in quotation marks, in holographic models. And the strategy is very simple. The strategy is just set up at the boundary. What you would like to study is what a bubble of the stable phase will do once you let it go, surrounded by the metastable phase. But we can map that problem to a problem in which we have some asymptotic horizon sitting at the bottom, corresponding to metastable phase, and some deformation of the appropriate deformation of the horizon that corresponds to the bubble. So once you set up these initial conditions here, then you just do time evolution of Einstein's equations, you solve the problem here, and then you read off the answer. You translate back to the gauge theory. So what I'm going to show you is the result of that calculation. This is purely information at the boundary. So this is the energy density, this is position, and when I click, this is the initial bubble. When I click, you'll see the time evolution, and this all comes from translating back a time evolution of the five-dimensional Einstein's equations in the bulk. So this is what you see. The bubble starts growing. It pushes the fluid in front of it out of equilibrium, and it forms this front. By energy conservation, all the latent heat that you're gaining by going to the stable preferred phase has to be accumulated in front of the bubble. So simply by repeating this process for different nucleation temperatures, you can get the velocity as a function of some parameter which is a proxy for this temperature. And in this case, if you choose appropriately this parameter, you get a very simple relation, and one of the things that we are investigating is whether this is actually robust and more general than just the model that we looked at. But of course, if you have a single bubble, because when it expands it's spherically symmetric, this will not produce any gravitational waves. In order to get production, you need bubble collisions and all the subsequent interesting dynamics. So here's a simulation of the collision of two bubbles, just to show you that this can actually be done. And one of the interesting aspects of approaching the problem from this perspective is that all the post-nucleation dynamics of the bubbles, including the expansion, the collisions, all the sound modes they leave behind, even the possible appearance of turbulence, which is supposed to also give a contribution at late times in cosmology, all of this is included in this discussion, or in this description, at least potentially. Okay. In the interest of time, let me now move to phase transitions in neutron stars. So that was the cosmology part. Let me talk about astrophysics a little bit. So when two neutron stars collide and merge, it's well known that you get a signal like this. This is the strain that you get. It's a, if you're not familiar, it's just a measure of the strength of the gravitational wave that reaches us. This is for a merger happening at 100 megaparsecs from Earth. Of course, the further away, the weaker the signal. So what you see here is the initial in spiral, where you can think of the two neutron stars as point particles. Once they are close enough, they start deforming each other through tidal effects. That's this part of the signal. And then once they merge, you get all the interesting, for me, all the interesting and messy physics, because these are two blobs of fluid, 10 kilometers in size, and they do lots of interesting things. So with the Einstein telescope, so LIGO missed, this fell outside the band for LIGO, but with the Einstein telescope or the Cosmic Explorer, we'll be able to see this even actually to the end of the visible universe. Okay, so every single merger in the universe will be detected potentially by these new detectors. So one thing I want to emphasize is that if you look here, you see that the characteristic frequency is in the kilohertz. Okay? However, suppose, after all, neutron stars are really good laboratories for QCD physics, okay, in extreme conditions that we cannot recreate on Earth, like high density, high baryon density, for example. So suppose that QCD has a first-order phase transition in its phase diagram, such as a transition between hadronic and quark matter. This is something that pretty much every effective model for QCD predicts. Of course, they don't agree on exactly where the transition is, but they all tend to give such a first-order phase transition. But establishing this, either experimentally or theoretically, has resisted analysis for decades. This is one of the most important open problems in nuclear and particle physics, okay? And even heavy ion collisions have not yet given conclusive information about this, but neutron stars could. And the reason is that people have done magnetohydrodynamic simulations coupled to GR of the merger, and with an equation of state, which is an input in these simulations, with an equation of state in which they include a first-order phase transition, just to see what would happen, okay, according to the theory. And what you see is that because when these two objects merge, there are regions of the star that get heated up or compressed, some of the matter in the star gets pushed from the hadronic phase across the phase transition. Okay? If you compress it or heat it up, you push it across the phase transition. So it's the opposite of what happens in cosmology. In cosmology, you overcool. Here, you overheat. Okay? And these are kilometers in size. Okay? Now, this is known to give a modification to this kilohertz signal, but this modification cannot distinguish between a first-order phase transition and a rapid crossover. Okay? And the reason it cannot is because in this analysis, nobody had included the dynamics, the precise way in which the phase transition takes place, which is this nucleation of bubbles. So the idea is that you have some region of the star, this is just a small region, a few kilometers in size, in which the hadronic phase, for example, has been pushed and overheated into, it wants to go into the quark matter phase. But the way it goes is first it reaches a metastable state, and then it starts nucleating bubbles of quark matter. And then these bubbles grow and collide, and the characteristic size of the bubbles when they collide gives you the characteristic wavelength of the gravitational waves that you produce. So this is very much like the same story as in cosmology, but instead of overcooling, overheating. Okay? Of course, once you've overheated, the stars keep moving around, and this will also cool down back, so you get several cycles of production. Okay? But the crucial point is that you can very easily estimate this characteristic wavelength, and it turns out to be half a kilometer, which if you translate to frequency is almost a megahertz. Okay, so there's the primary signal in the kilohertz, that's well known, and this is a new prediction based on only standard model physics for a megahertz signal in in neutron star mergers. And potentially, this could be detected if you do an estimate of the amplitude of the signal that we could get. This could be detected with future detectors, not today, but with future detectors, for example, superconducting resonant cavities, at tens of megaparsecs from Earth. And this is interesting because the first detection in 2017 was at 40 megaparsecs. So this is not out of the question. And what's interesting about this is that, like I was emphasizing, this is the only known signal in the megahertz range coming from astrophysics using only standard model physics. Okay? And for experimentalists, this is crucial. They want to know that there's something that does not rely on speculative physics that should be there, okay, if they have a detector that's good enough. And the second aspect is that this gives direct experimental access to whether or not there's a QCD phase transition. Because if there is no phase transition, if it's a crossover, there are no bubbles. And if there are no bubbles, there is no out of equilibrium physics, and there is no megahertz signal. Okay? Good. I think I'm doing okay with time. So let me now move on beyond this approximation in which you're looking at this matter doing interesting things in a fixed background. Okay? That's what I've done so far. I've shown you how to describe out of equilibrium quantum matter, for example, in these phase transitions, in a fixed Minkowski spacetime. But there are lots of problems that require going beyond that. For example, if you really want to think about cosmological phase transitions, the spacetime is not fixed, it's expanding. All sorts of cosmological defects, neutron stars. You can think about inflation, pre or reheating, primordial black hole formation, etc. In all these situations, gravity is dynamical. So what we need is a framework in which the boundary is no longer a fixed background, but is also allowed to fluctuate in response to what the stress tensor at the boundary is doing. Okay? And vice versa. The stress tensor has to be sensitive to the dynamics of the metric. So basically what you want is a framework in which the stress tensor, or the expectation value, this is what's called semi-classical gravity. In semi-classical gravity, gravity is classical, so it obeys Einstein's equations. These are the four-dimensional Einstein's equations at the boundary, coupled to the expectation value of the quantum stress tensor. Okay? So the idea is to modify holography in a way that the five-dimensional description gives you the dynamics of the stress tensor, as usual, and then you evolve the four-dimensional metric according to the four-dimensional Einstein's equations coupled to this stress tensor. But because this four-dimensional metric is nothing but the boundary value of the five-dimensional metric, this is actually a coupled problem. It's a 4D, 5D coupled problem. Okay? And this makes it hard. Nevertheless, we have already applied this to several situations with a lot of symmetry, like at the Sitter dynamics at the boundary, inflation and reheating has been applied by other people, and also to Kastner spacetimes with the goal of understanding cosmological singularities, quantum field theory near a cosmological singularity. But what I want to do today is actually, if you think about it, if this framework makes any sense, once you have dynamical gravity at the boundary, the hallmark of having dynamical gravity is the possibility of gravitational collapse. Okay? So what I want to show you is that you can actually use this framework to simulate gravitational collapse at the boundary. Okay? So metric is dynamical at the boundary. So the starting point is consider now a homogeneous thermally equilibrated fluid at the boundary, like we did earlier. So if you don't have dynamical boundary at the gravity, dynamical gravity at the boundary, this would simply correspond to a static black hole sitting at the bottom of our geometry. But once the metric here is dynamical, if you fill it up, if you fill your space-time with a fluid, this will back react and you will get an FRW-like geometry, okay? Which is what happens here. But then in the bulk, what you get is a receding horizon, because remember, in FRW, the universe is expanding, the temperature and the energy density are decreasing. So in the bulk, the position of the horizon is telling you, is a proxy for the temperature. So if this is expanding and cooling, this will actually give you a receding horizon, okay? This was well known. But now suppose that you put some small overdensity here. So you prepare inertial conditions in which asymptotically you have this FRW geometry, but in the center you put some overdensity big enough so that it will lead to gravitational collapse. This is literally what people thinking about primordial black holes think all the time. Okay? So in that case, now you have to solve the 5-dimensional equations coupled to this initial, with these initial conditions and coupled to the dynamics here, and that's hard. But one thing that you can do is go to a limit in which this can be described as a fluid, which is, thank you, which is, again, what people do in primordial black hole formation do, okay? And the reason that's really helpful is, actually there are two reasons. One is that you can solve the dynamics here independently from the bulk, because now you don't need to predict the stress tensor with the bulk. And once you have solved the problem here, you can use the fluid gravity correspondence to actually construct the 5-dimensional metric, okay? In the approximation, which this is well described by a fluid, then you can use this duality in the fluid approximation to construct the solution. And what you find is that as the matter at the boundary begins to collapse, part of the horizon asymptotically is receding, but the region near the point where the collapse will take place starts growing. The horizon gets deformed. It keeps going, and once this collapses here, that's exactly the time when this sort of funnel that you have formed touches the boundary. Okay? That's exactly at the same time. So over here, what you've done is to produce gravitational collapse. This is the point where the event horizon is born at the boundary. And that's exactly the point where the black funnel touches the boundary. And to me, this is a strong indication. You can follow the dynamics. And one thing that one question you could ask me, to which I don't know the answer yet, is whether this will now, if you follow the evolution for longer, initially what's going to happen, and this is what we see, is that the horizon will grow, and it will it looks like it's saturating at some point, because everything around it is diluting because of the expansion in FRW. But at some point, you expect the black hole horizon to actually evaporate, okay? Because this is dynamical gravity coupled to quantum fields. So I don't know the answer to that yet, okay? Stay tuned. But the fact that you can describe gravitational collapse in a consistent way from the bulk as well, to me, it's a strong indication that this framework actually captures the correct physics. So thank you very much, and I'll take questions now.
All right. David has been very good on time, so we have lots of time for questions. Carlos.
So, very nice, David. Let me ask you a couple. When you had this situation with dynamical gravity, right, and the field theory out of equilibrium, what do you calculate there? What are the correlation functions that are of interest to calculate?
The first one is the one-point function. So, for example, one thing I didn't mention, but which is published work with Chandra, who's in the audience, and Jorge Casal-de-Rey, is you can ask questions about what happens to the stress tensor of quantum fields near a cosmological singularity. Mm-hmm. So you can take a Kastner metric at the boundary and ask what happens to the quantum fields when you approach it. And then once you know that, you can back react on the metric and do the full system. So the hope there is that the behavior of the quantum fields is different, and it may alter the whole BKL story near the singularity, for example. So to answer your question, the first thing you want to know is the one-point functions. But you could also look at correlations, higher point functions.
And you calculate with the usual holographic prescription.
Well, if you want higher point functions, then it's hard because it's a time-dependent background in the bulk and so on, but in principle it can be done. Yeah.
The part of the dynamical gravity, basically you are putting a cutoff in ADS?
No.
Okay, good.
Thank you for the question. Yeah. I should have said that, but I was worried about time and a strict chair. So this is not a brane world situation. I cannot overemphasize this. Okay, there is no explicit UV cutoff. This is really dynamical metric at the boundary. There's no UV cutoff. However, if you take a CFT at the boundary, which is UV complete, and you couple it to classical gravity, this setup is no longer a UV complete setup. Okay, because gravity comes with a Planck scale, and in fact, if you couple it to a large N theory, then the cutoff is what's called the species scale. So you should think of this gravitational plus quantum fields at the boundary as an effective theory. But as long as you understand this and you're below the cutoff in curvatures and energy densities and so on, it's a well-defined setup.
Other questions? Kostas has a question behind you.
Yeah, I think that's a follow-up
So the metric is a non-normalizable mode in ADS. How did you make it dynamical?
Because what you do is you change the boundary conditions.
This doesn't affect the issue of the fact that the metric is non-normalizable.
No, it does. It does.
You mean go to mixed?
It's mixed boundary conditions, yes. It goes back to this paper by Don and Jeffrey Compare, setting the boundary free.
Sorry, I wanted to ask, is there any, just back to the phenomenological part of the problem. So is there any like a smoking gun imprint in the shape, the transfer frequency for like the phase transition? Or is it only like the rough idea where there is the frequency that like the signal peaks? I was just wondering, or I mean, maybe the second part of the question is that, I mean, are you aware of any model or maybe some strange gauge theory in which you can actually like exactly predict like the signal due to the phase transition because of some simplicity of the setup?
Okay. The short answer to your question is that predicting this exactly is an incredibly difficult problem because you need, but it has nothing to do with holography. Even if you could solve quantum field theory, you have to go from a homogeneous initial state to the nucleation of bubbles, which is probabilistic, to the subsequent evolution, the collisions, the sound modes they leave behind, and so on. So what people do, and I think it's the right thing to do, is to try to understand the spectrum of these sound modes that are left behind, because that's what's produced in the gravitational waves. And there's some distribution that people have managed to understand in more or less detail over the last 30 years. Okay? And it does give this double broken power law spectrum in which you have some peak at some point and then it decreases exponentially away from that peak. But one of the things I want to emphasize is, I also didn't mention, is that in that community, for a very long time, they have assumed something, I don't want to get into the details about the equation of state, which is not general. So this picture they have of the bubbles colliding and leaving behind sound modes, little sound modes that produce gravitational waves, may not be actually applicable to strongly coupled theories. In strongly coupled theories, the dynamics may be very different. This has nothing to do with holography, but the only way I realized about this is by thinking from the holographic perspective. So that's another way in which this is useful. It gives you a new perspective on all problems, and I'm excited to see if this actually gives a different spectrum.
Okay, a question in the back there. Let's take this one first.
On one of your slides, you had like a picture of a black funnel, but it was in ADS5. So, and there was this paper by Hubeni and other people. Do you have like a 5D version of the ADS-C metric?
No, no. The C metric is analytic, but nobody prevents you from finding these solutions numerically. But I don't have an analytic analog of that in 5 dimensions. No, this is numerical. In fact, it's an approximate solution because it's constructed in the limit in which the fluid gravity duality applies.
See, okay.
But in principle, you can construct it exactly numerically.
So is there any reason you don't look at second order phase transitions? For example, in the cosmological context, you could imagine a quench, and that could lead to very interesting effects.
Second order phase transitions don't take the system out of equilibrium. And that's the reason why they don't produce gravitational waves in a significant amount. They could be interesting for other reasons, like, for example, formation of defects.
Yes.
You still form through the,
For example, if the
mechanism.
universe is cooling fast enough, then you could imagine producing instabilities. Then you're trapped in the wrong phase, the spinodal instabilities.
Ah, good.
Yeah.
So we have a paper on that. But in order to get there, you need to suppress the nucleation of bubbles. So to get to the spinodal, you have to traverse the entire metastable region, as you know, okay? And there is where the system wants to produce bubbles. So you need to suppress that production somehow, and large N is one way to do it. But if you take a realistic N, it's very difficult to suppress it enough. Basically because of the separation of scales between the Hubble scale and the local temperature, which is given by the Planck mass.
Okay, well, I think in view of time, we'll stop there, and thank David again.